Hi everyone, welcome to my presentation. I am Mao Mao from Professor Chi Min Chi's group, the Department of Chemistry at Hong Kong U. I am very honored to attend the third International Conference on Material Science and Nanotechnology. And today I want to talk about the stable, high-efficiency, voltage-dependent color-tunable organic light-emitting diodes with a single Tetradentate platinum 2 emitter having non-operational lifetime. In today's presentation, there are four parts. The first, I want to introduce the background of OLEDs, and then I will explain why we choose color-tunable OLEDs. Here, I will emphasize the potential application of color-tunable OLEDs, and then I will comprehensively show you our color-tunable OLEDs with single PT2 emitter. The high efficiency and long-operational lifetime will be emphasized. In this part, I will also discuss the mechanism of color-tunable OLEDs with single PT2 emitter and display the high device performance of our color-tunable OLEDs. And last, I will summarize our presentation and outlook the application of color-tunable OLEDs. Let's move to the first part. So what is OLED? OLED is abbreviation of organic light emitting diode. Is a LED in which the emissive layer is organic compound or metal complex, as the picture shows. In 1987, the first OLED was reported by Professor Tang. It was actually fluorescent OLED with 25% internal quantum efficiency. In 1998, both Professor Chi, Professor Ma, Professor Stephen Forrest, and Mark Thompson reported the earlier phosphorescent OLEDs. For this type of OLED, the IQE can achieve almost 100% in stereo. And this type of OLED is actually being commercialized. And after 2009, other types of OLED can also achieve 100% IQE, such as thermal activated dilated fluorescent OLED and thermal sensitive dilated fluorescent OLED. And then I will explain why we choose OLED. Because OLED has flexible and ultra-thin characteristic. It is actually the solid state and area light source, and is also energy saving like LED. Here I want to give you a general impression on OLED device structure, as illustrated in this picture. In general, OLED has basic three layers. They are anode, cathode, and emissive layer deposited on the ITO substrate. To make the device performance better, we always add the whole injection layer, whole transporting layer, electron transporting layer, and electron injection layer between them. And when apply the DC voltage, the electron and the hole will generate it at the cathode and the anode respectively, and then they will go into the emissive layer to form exciton and emit light via radiative decay. At present, OLED has been used for cell phone, TV, and smartwatch. They can be also used in OLED lighting field. It is estimated that the global OLED display market will be increased from over $4 million in 2020 to $18 million in 2026 by the rate of 23%. That's a huge market and it's very promising. Then I will tell you how to evaluate OLED. We always evaluate it from three aspects. The first is device efficiency. We always use external continuous efficiency (EQE), the current efficiency, and the power efficiency to evaluate. Without outcoupling, EQE max can be up to 13%. Then we use efficiency of. In general, for display, the OLED always work at 100 to 1000 cd per square meter. For all the lighting, the luminance will be higher. We can calculate it from this molecule. And then the operation lifetime is much more essential for practical use. Here we use the LT lighting to calculate its operational lifetime. The LT lighting will be mentioned below. Then I will explain why we choose color-tunable OLED. Because color-tunable OLED can be used for decoration, smart lighting, as the picture shows. And what is more, it can be used for functional sensors, such as the display for ECG sensors referred to this article. As we know that the first color-tunable OLED was reported by Mark Thompson and Stephen Forrest in 1997. They actually used 3 color emitters. Up to now, there are 5 types of color-tunable OLED as illustrated in this picture. For type A, B, C, and D, they actually use 2 or more emitters. And up to now, there are still some challenges for color-tunable OLED. The color tuning range should be wide, and the color tunable OLED device efficiency should be high. And what is more, the device stability is not ideal now. We can improve the device structure and emitter stability, and compared to the common OLED, the color-tunable OLED has another problem of color aging issue, which is caused by the multiple emitters with different working lifetimes. And is there a single emitter with multiple emission? Of course, yes. Thanks to our previous work. The planar PT2 complex has both monomer and aggregation emission with different peaks. So is it possible to fabricate color-tunable OLED with single PT2 emitter? If that, the color aging issue could be solved perfectly and the device stability will be improved a lot. Then we propose a hypothesis. As we know that there are 2 energy transfer passes. One is direct energy transfer, the other is charge trapping in the OLED. When applied low voltage, the exciton will preferentially come to the aggregated site with lower energy level. As a result, the aggregation emission will dominate it, and the color will be red. When increase the voltage, the aggregated site will be saturated and more exciton could come to the monomer state. As a result, the monomer emission is gradually enhanced and the emission color will be green. Based on the hypothesis, we fabricated a color-tunable OLED, and the device structure and chemical structure of organic materials are shown below. Here we fabricate 2 devices. One is doped with low doping concentration. The other is doped with a higher concentration of 12%. The EL spectra of these 2 devices are shown below. We find that device B with a higher doping concentration has wider color tuning range. Then we use Gaussian fitting to estimate the real ratio of aggregation emission to monomer emission. We find that device B has wider color tuning range. Then we use trapping and energy transfer model to verify our hypothesis. The formula is as follows. I just simply show to you. This is the experimental data and fitting curves. I want to draw your attention to the device B. We find that device B will match the model with higher real R square of 0.96. To get better color tuning range and device performance, we use co-host in double emissive layers device structure to fabricate. The structure is shown as below, and as a result, higher EQE max of over 20% and low ROF at 1000 CD per square meter and wider color tuning range are achieved. And then we use another emitters PTX2 and PTX4 to fabricate color-tunable OLED with the same device structure. And the key performance of device are shown below. Here I want to draw your attention to the device of PTX4. We find the higher EQE max of 23.23 and wider color tuning range are successfully achieved. Here is the published results for these three devices. In Figure A, the CIE changed with the increasing voltage for these three devices. In Figure B shows the low ROF and high efficiency of these three devices. Then we go on to test the device operation lifetime with this device structure. As a result, almost 20,000 hours are achieved at a luminance of 100 CD per square meter for LT lighting. The LT lighting is calculated according to this formula. But the EQE max of these devices are below 10%. Then we further to optimize the device lifetime and efficiency. Here we use SFBCZ and SFTRZ as co-host. As a result, over 15,000 hours can be achieved at a luminance of 100 CD per square meter for LT lighting and 13.8% EQE is also achieved. Much longer operational lifetime for our improved device. And then we use another emitter to fabricate color temperature tunable white OLED with single emitter. As a result, the color temperature can be tuned in a large range, and the color can turn from warm white to cold white along the blackboarding radiativity curves. Finally, I want to summarize our presentation. We fabricate color-tunable OLED with single Tetradentate PT2 emitter, including the color temperature tunable white OLED. We achieve the high efficiency, the wide color tuning range, the device stability at the same time. And then we discuss the mechanism of color-tunable phenomena with trapping and energy transfer model, and verify our hypothesis. At last, I describe the application of color-tunable OLED, such as smart lighting and biomedical sensor. Because of the good performance of our color-tunable OLED, here I want to emphasize that our color-tunable OLED can help the biomedical sensor for health visualization. At last, I want to thank Professor Chi Min-chi, Dr. Chen Gang, and other colleagues of our group. And then I want to thank Professor Xu Sijie in Department of Physics of Hong Kong U. And this work are supported by Guangdong Project, Shenzhen Project, and Innovational Technology Function in Hong Kong. Thank you for your attention. We expect for further cooperation based on our color-tunable OLED. Thanks again.